Hi, I'm Angad. I'm the engineering lead for Team 971, and I'll be talking about our 2025 design philosophy and robot overview. Okay, so to start, let's go over some of our old robots. So in 2023, we had a really good robot up until Champs, where we had problems with our end effector. It was pretty unreliable and broke often, which led to a not so great Champs run. And before Champs, we actually had a more reliable end effector designed, but it was never implemented due to like the complexity of the set points. I think we had over 45 set points that would have had to be changed, and we simply didn't have enough time for that. Another year, 2024, we had a robot with a turret and a catapult, as some of you guys may know, and it had many handoffs and an unreliable or overly complex architecture. And if one thing broke, nothing would work. So for example, we had our intake, transfer, and extend, and we needed the note to pass through all three of those subsystems before entering the shooter. So if one of those broke, we basically couldn't do anything during the whole match. So what did we learn? So what made 971 971? It's like cool and complex robots that no other team made, just couldn't compete with top teams anymore in this new age of FRC. And we also lost many mentors, and we just simply didn't have the resources anymore to make those same robots. So we had to change our design philosophy to focus on simpler robots. And that leads to the question, how did we design our 2025 robot for simplicity and reliability? So our main goals going into the season were to make it as easy as possible for software. So this meant eliminating overly complex designs, and this is because if we were to design a 5-DOF arm like 2023 this year, we just simply wouldn't have been able to code it. We also wanted to minimize match any failures, and this meant mechanically designing for as few handoffs as possible. And this is kind of why we avoided a funnel design from Human Player Station this year, or like a full ground intake where we would intake from the ground intake. We also wanted to focus on getting the important parts of the game right first. So we actually ended up CADing pretty much all of our superstructure before we started on our climber, because we were thinking that we wanted to focus on coral and algae scoring first before we focused on endgame. So one more thing we did this year to help us achieve our goals was iterating. In the past, we generally would design a single robot and stick with that design, maybe some few minor tweaks. However, this year, we decided to focus on iterating. So we did this by making 2 robots. So one of them we took to our first regional, which was Ventura, and we made a second robot that we took to our second regional, which is CVR, Central Valley, and we also took it to we took it to Champs. And we also wanted to get the robot framework done really quickly. So I think we CADed and built our first robot in a record amount of time this year, so that we had as much time as possible to start focus on iterating. For example, we had approximately 6 end effector iterations and 4 climber iterations throughout the season, and many of our other subsystems were iterated onto. So now I'll just go through our robot. I'll go through all the different subsystems, starting with drivetrain, elevator, and pivot, and then our arm assembly, which was like the arm itself, wrist, and end effector, and then I'll go into the climber and our ground intake, which was a late addition after both our regionals before Champs. So to start with our drivetrain, as many of you guys know, we didn't do a tank drive this year. So this is our first year running swerve, and we were running WCP X2i swerve modules and a very basic drive base. We had a wood belly pan and 2x2 aluminum tubes with a 1/16 wall. And we also had cutouts in the belly pan for access to things like elevator gearbox and the sprocket. This is just designing for serviceability. Another cool thing we did is we had TPU camera lens hoods and covers for the encoders on the swerve modules, and these worked out really well. At first we had, I think, PLA covers, and those didn't work great. And we also tried PETG, and TPU worked great. Moving on to our next subsystem is our climber. So I'll go over our first iteration first. So The last few games that had an elevator in FRC were 2018, 2019, and 2023. But 2 of those years we actually made a double jointed arm instead of an elevator, and one of those years we made a carbon fiber elevator that just wasn't applicable to this game. So we didn't really have much experience with elevators going into the season. So we decided to model our elevator off of the WCP Gray T cascading elevator. And for those of you that don't know, a cascading elevator versus continuous, in cascading, all the stages move together. In a continuous elevator, the one stage moves at a time. So for example, the carriage will move first, and then it will engage the first stage, and then that will all move. And we started off with the number 25 chain, driving it, and we had problems with the chain skipping. So to fix that, we switched to a number 35 chain, and we moved our encoder to the top shaft. And that really helped with the skipping problems. We also had some problems with stiffness, so we ended up adding these stiffener tubes on both sides, and those helped a little bit. Moving on to our second iteration. So we wanted to reduce weight following our first regional to make weight for a ground intake. So we designed a lightened elevator that was around 10 pounds lighter, and we did that by lightening a lot of tubes like the first stage tubes. But at first, it had terrible stiffness. So after we made it, we tested it out, and we just couldn't score L4. It took super long for it to stop shaking before we could score. So we ended up redesigning it again, kind of. And what we did is we added a diagonal support tube like this one. And we also added these plates to keep the elevator tubes from bending outwards at scoring positions like L4 scoring. We also removed some of the lightens. For example, this section of the tube right here, we removed the lightens because that's where we were scoring L4. And we also supported, we also increased the thickness of this tube over here to 1/8 inch wall, the cantilevered part. And the main thing that really helped, I think, was the diagonal that I talked about earlier. And it helped the elevator not start parallelogramming, which means like kept it more rectangular. Okay, so going more in depth into our stiffening. So this is the tube I was talking about, this aluminum tube, and it was a 0.75 OD 1/16 wall thickness tube, and it worked well. So how we did it is we had the tube, and we had these eye bolts, this orange piece right here, and we had a tube nut that was cut on the lathe and then epoxied into the tube, and we screwed the eye bolt in, and on one side there was a left-hand tap, and on the other side there was a right-hand tap. So when you tighten the tube spacer, when you tighten the tube support, it would tighten the whole thing and bring them closer. And we also use these jam nuts over here to keep the tube from unscrewing. So while that worked well, in the off season we realized we had some weight. So we ended up switching our stiffening, and we ran sheet metal and a 2x1 tube, and it worked amazing. So although it was 2.2 pounds compared to the 0.8 pounds for the tube support. And in the future, if we were to do the stiffening again, we would still go with the tube support, but we would probably use a larger OD tube and try carbon fiber. This is because we tried carbon fiber this year, but we didn't use a large enough diameter tube for the carbon fiber, and this led to just not being stiff enough. But if we had used a large enough outer diameter carbon fiber tube, I think it would have worked really well. Okay, moving on to our next subsystem, I'll talk about our pivot in the first iteration. So for the bearings, we used 6810 RS bearings, and these are what we used on our 2023 arm. So we had them lying around, and they might have been a little over-spec'd for this case, but they worked well. We also used these 1-inch OD tube spacers, and we used tube nuts in them, and this provided a very stiff setup. So we needed to space our whole pivot away from the elevator by a certain amount to make room for the end effector to pass over. And this is probably one of the best solutions for that, since it created a pretty rigid subassembly. We also had a 1 to 106 reduction, which is kind of an overkill and we had an X60 on it. And to keep the cables, we use an IGUS. Yeah. So going into our second iteration. So this one was 25% lighter, and we got rid of a stage in the gearbox and reduced the reduction from 1 to 106 to 1 to 96 with still an X60. And even still, it was over-spec'd. We never hit our current limits, or I don't know if we even got close to them. One more cool thing about this is since we were using our old AOS software, we still needed magpots and encoders. And the way we did it is we used something called a magpot assembly. So this thing is, so we ran a pulley off of our pivot shaft, and that came over here. And we had an encoder in one side, and a potentiometer in the other. And this led to a pretty simple way of measuring both those, implementing both those sensors. So we used a polycarbonate gear for our pivot to transfer the load to actually moving the arm up and down. So we used 110 tooth 10 dp polycarbonate gear, and to decide on what material to use, what size to use, we used the Lewis equation, which measures the bending stress, or it measures basically how much load a tooth of a gear can handle. So to do this, we started with the yield strength of polycarbonate, which is 11,500 psi. And from there, we got the maximum bending tooth strength, which is around 3,800 psi, which is 1/3 of the tensile strength. And the face width of the gear, we chose to use a 3/8 gear. So that's just 0.375. It's a 10 dp gear, which is the diametrical pitch of the gear. And the Lewis factor, so this is a constant that we found it online. It relates the amount of teeth and the pressure angle of a gear. So in this case, it was 0.368. And if you put those together, you get a 52.9 pounds max tooth load, but then you have to multiply that by the radius. And that gets you to 265 pounds approximately as the max load on the gear, which we determined was sufficient for our case. So you might have noticed that I'm doing calculations for a 100 tooth gear, even though we used a 110 tooth gear. We originally calculated for a 100 tooth gear, but switched to 110 for gear reduction and packaging purposes. So we also, in the beginning, looked into the deflection and friction on the gear. We were scared that maybe the friction would cause the polycarbonate to overheat, or the deflection would cause the gear to snap. And we determined that both of these were insignificant. Like, for example, the friction, we determined that the temperature of the polycarbonate would get nowhere near high enough to where it would be a problem. Also, to determine lightening, we used on-chip simulations. And in hindsight, we could have lightened more. We had an overkill factor of safety. And we never had any problems with the polycarbonate gear throughout the season. I think we used 2 gears throughout the season. We could have used 1. There weren't any problems. And if a tooth chipped, we could still run the mechanism and there wouldn't be any problems. Okay. Our pivot arm, so our whole arm assembly could slide out, and this really helped with serviceability. So if we had a problem, we could just take our whole pivot arm out by removing one snap ring. And for the pivot shaft, we used a 2-inch outer diameter, 1/8 inch wall thickness tube. And the reason we chose such a large OD tube is because as you increase the diameter of your shaft, you get a lot better bending and torsional stiffness. This is because those are scaled by because one of the factors in that equation is the polar moment of inertia, and that is scaled by diameter to the power of 4. So there's an exponential increase in stiffness as you increase your diameter, while the weight doesn't really increase that much. To transfer the load between the arm, the gear, and the plates between, we used a mix of dowel pins and bolts. Dowel pins are really good at transmitting load, and bolts were there to keep everything together. Okay. So our wrist, it was a dead axle this year, and we also kept an encoder on the pivot axle so that we wouldn't have any problems with belt skipping, which I'll get into later. And we made this gearbox out of polycarbonate, mainly because of weight reasons, like much of the rest of our design. We had a 1 to 20.5 gear ratio, which was under spec, but it didn't lead to many problems. When we would move our arm with algae in it, it would flop, but it didn't lead to too many problems. Yeah, and it was an X44. So we also wanted to keep our gearbox closer to the pivot point, and this really helped with keeping the center of the mass closer to the pivot part so that it would require less torque to move. And that meant we would have to have a belt or a chain connecting to the end effector, and we chose to have a belt because of the weight, but that meant we had to make sure that a belt would be able to handle the loads. So that's why we chose belt. Okay, anyways. So we determined that the weight with coral of the end effector would be 8 pounds, and we figured out how much torque we would need to move the end effector. And from there, we got this table, which you can find from the Gates Power Manual. And what it tells you is, it tells you how much torque each pulley is rated for. And they also provide you with a multiplier for a 15 millimeter belt. So if you multiply these values, which tell you the number of grooves, by the multiplier, you can get how much torque it's rated for. So we kind of listed out a bunch of different possible pulley diameters, and from there, we figured out their rated torque at 15 millimeters for the belt, and we determined that a 48 tooth pulley would be sufficient for what we needed. And from there, we figured out the driving pulley, since that was the driven pulley, and we determined a 15 tooth driving pulley would be sufficient. So that led to our pulleys. So we did have some problems with the belt skipping, but we added a redirection idler here that helped give the belt more wrap around the pulley, which helped. And we also had an encoder on the output shaft, which meant that any belt slipping was kind of not important. Okay, so now going into our end effector. So our end effector went through many revisions. It was probably what we changed the most during our season. So we started off with this design. So when we were choosing this design, we wanted to avoid handoffs. So we wanted something that could intake directly from the human player station and intake from the ground. So although this design wasn't great at intaking from the ground, when we chose it, we thought we'd be able to get a pretty decent ground intake from just the end effector itself. And that's kind of what led to this design. So we started with this more like shorter shape, and then we switched to this design. And the star wheels really helped with intaking coral from the ground, but it meant that we could barely hold algae anymore. So we decided to switch back to this design. So yeah, we were basically just changing the shape and wheel configuration throughout, and reliability. We were changing different things. This led to our final iteration. So one of the main things is we moved the gearbox. So as you notice over here, the gearbox is on top, and we got rid of that, and we managed to move the gearbox, or like all the gear stuff, down there. And what that meant is it really led to fewer reliability issues, since that print sheared multiple times with the old revisions. So we also used WCP SRPP, which is a material similar to Max Composite. It has a way higher impact resistance than polycarbonate while being lighter, so it's really great for applications like this. And we also used it on our ground intake, which I'll get into later. And we used PTFE bushings since they're a lot lighter, and those work pretty well. These prints were made out of onyx, so we had no problems with them. And we also had a centering spike over here, and this helped the coral just like come in straight, especially from the ground intake. It really helped. We were running an X44 on our end effector, and we had a 1 to 16 reduction, and this pretty large reduction really helped grab algae. So lower reduction was better for coral, but we needed to find compromise with the algae. So our climber. We started off with this system where we had the latcher below the pivot point, And this actually worked really well for actually climbing. The hard part was we found it really hard to latch onto the cage with this system. So at first we tried just adding these little like guides, but those really didn't help. So before Ventura, our first regional, we switched to this style of climber where we were latching onto the cage above our pivot point. And this was like almost the same, almost as good as climbing, and it made it way easier to latch. So we stuck with that design into Ventura. And we also stopped using magnets on this one since we found that they weren't doing anything. So if you notice over here, at first we thought that magnets would really help like latch onto the cage. Okay, so this led to our final iteration, which was our wheeled climber. So we kept the last iteration for both our regionals, and we switched to this one before champs. So the way it works is there's two flex wheels that grab onto the cage and pivot, and it really makes the latching process really easy. So we switched to it after seeing teams like 254's climbers, which were really quick, and this ended up working really great, and we ended up having a really good climb at champs, and I think we could consistently climb within the last like 6 seconds of the match. So how our gearbox worked is, so we had rope going from here down to the gearbox, and it would wrap around this capstan right here, or sorry, wrap around this drum right here, and so the motor had a planetary gearbox, and it would spin and wrap the rope, and after the match, when it wouldn't unwind because there was a ratchet. So our ratchet was just a 1/2-inch wrench that had been cut down, and if you can see over here, there's a little lever that you could switch to change the direction. So after we climbed, to reset the climber, we would just flip the ratchet, unwind the rope, and then flip back into the ratcheting mode. And this worked really well, although it was quite heavy, this whole system with the planetary gearboxes. And both these X60s were on a 1 to 112.5 gear reduction each. Okay. So our ground intake was a pretty late addition to our robot, and it had a belt-driven pivot, similar to our wrist. We were determining between belt and 10DP gear to drop down the pivot, and we decided that belt would be easier to manufacture. And we were a little concerned about the load on the individual teeth if we ran 10DP gear. So that's why we chose belt. And these are Onyx prints, the pulleys. And we had a polycarbonate cross tube. And we connected that to each side using roll pins over here and here, over there. And these help transmit the load between both sides. And this is on a 1 to 20 gear ratio, which might seem low, but it was fine given that our moving ground intake only weighed 4 pounds. Yeah, and we also tensioned our belts for the pulleys with a off-centered idler. So what that means is like we had a circular shaft with a off-centered hole drilled through it, and we would just rotate it to create tension on the belt. So we determined that polycarbonate would be a lot lighter than a 1/2-inch aluminum hex shaft, even though it would be less stiff. We determined it would be fine. So how we determined the torsional stiffness is we use this equation over here, and then from there we determined the angle of twist. So to find KT, we started by determining the polar moment of inertia, J, which is just pi over 32 times the outer diameter of the tube, which is 1.25 to the power of 4, minus the inner diameter of the tube, which is 1.125 to the power of 4, and that gave us 0.0186. Then we found the shear modulus for polycarbonate, which is 345,000 psi, and the length of the polycarbonate roller was 25 inches. And from that, we found KT to be 257 pound-inches per radian. And from there, we calculated the angle of twist from one end to the other when we were applying a certain amount of torque, which we set at around 48 pound-inches. So that meant it would be twisting 10.7 degrees. So we determined that that would be fine given how kind of floppy our intake was. So that's why we chose polycarbonate. So going into our ground intake, we had 2 iterations once again. So the first iteration over here, which can be seen over here, it was done before our second regional, but we took it off the robot before going there since it did not work. And this is our intake that we had at Champs that worked pretty well. So our first iteration of the ground intake had a single roller and a ramp. So this really struggled at picking up coral from the ground, especially anything that was more than like 20 degrees, like so that anything like more head on just wouldn't go in since there was no roller at the bottom to help push it in. So we switched away from that into this system, which is somewhat similar to what other teams had given the front 2 rollers, and we had our end effector. So this would pick up coral off the ground and just put it straight into our end effector. So we had a pivoting top plate, and this helped with the head-on coral. So that eliminated that problem, and it worked pretty well. If it ever got jammed, we would spit our end effector a little bit, so just reverse the wheels, and then it would almost always just intake it right the next time. And we had a redirection over here using 3D printed gears, and we had a Kraken X44 right over here. We also had an aluminum tube across the bottom that helped with just a little more rigidity since it was extremely floppy. By the way, these are 1/8" SRPP plates, so yeah. Okay, one cool thing we did this year was our roller hubs. So in the past, like 2024, this is the shaft for our roller hubs. It had multiple lathe features and a mill feature, which is right over here. So these were a pain to manufacture compared to this year's shaft. This year's shaft is just this. It's a one piece of 3/8 Thunderhex shaft that's cut to length and tapped on both sides. And the way it works is, so we have it in our roller hub right here. And then once you want to undo this bolt that attaches it to the plate, you take a long screw and screw it in over here into this nut. And it presses against the shaft over here, and that kind of locks the shaft into place. And from there, you can unscrew and rescrew this bolt, and then you just take out the big bolt, and you can put a small one in to attach it to the tube. And this is what it looks like from an isometric view. Thank you.